So let's look a little more generally at what we can do with this idea of discrete probability. I've generalized the question somewhat from last time. Instead of considering just 2 dice, I'm going to consider rolling n dice, fair again, and I want to know how likely is it that I get no doubles. So we saw last time we computed that the probability of getting a pair of doubles was 1/6, or sorry, was 1/6. So we can use a basic fact of probability, and we know that for n equal 2, the probability of no doubles is going to be 1 minus 1/6. The probability of not x is 1 minus the probability of x. So, okay, that's great. So we've got our chart started. We have room here. Let's think about if I just had 1 die. So I've got 1 die. What's the probability of getting no doubles? Well, I have 1 die. How many ways can I possibly get 2 that match? 0. There are no ways. I only have 1 die. So when n equals 1, the probability of getting no doubles is 1 because there's just no way to do it. So I'm guaranteed not to get doubles. Okay, well, what if I have 3 dice? So here I can think about what's the probability of getting doubles. Well, I didn't get it there. Ooh, I got double 5s. Maybe that was lucky. Ah, double 6s. Maybe that was lucky. Ah, all different. It seems like, okay, all different. And now I got double 1s. It seems like, so in those rolls, in those few trials that I did, about half the time, I ended up getting doubles, which is kind of interesting. But let's think about how can I compute what the probability here is when I have 3 dice that I'm rolling. Well, think about rolling them instead of all at once in your hand. Think about rolling them sequentially. So these 2 I haven't rolled yet, let's say, and I'm going to roll this one. Well, this one I'm guaranteed not to get doubles with the first roll. So I'm going to think about doing that. And now what's going to happen with the second roll? What's the probability that I don't get doubles? Well, to not get doubles with my second die, all I have to do is not match the first one. So, okay, great. And I actually did it there. So that means not matching it. We're back to this problem. So this is going to be 1 minus 1/6. Okay, and now let's bring in die number 3. So with this guy, what do I have to do in order to not get doubles? I have to not match the first one and not match the second one. Oh, fail. Ah, success. Okay, so here I'm saying there are 2 out of 6 possible rolls that I've eliminated. So that tells me that the probability of rolling 3 dice and getting no doubles is this. And of course I could write this another way. I can kind of ignore my 1. This is 5/6. And this is going to be 4/6. And there are 2 6s. So I can write it like this. 5 times 4 divided by 6 squared. Let's keep going. Let's think about what if I added another die? If I want to add another one, what do I get? What's the probability? How does it change? Okay, so I have to assume if I'm trying to get no doubles, then in the first 3 I got no doubles, and I know how likely that was to happen. Now I'm going to do another independent trial. Okay, so I'm just going to multiply the outcome. What's the probability that the 4th die that I roll doesn't match any of the 3 I've already rolled? Well, I can't be a 4, a 5, or a 3. So I've eliminated 3 of the 6 options. Ooh, bad. I have a 50% chance of getting it. And now I finally got it. Okay, so when I'm rolling 4, I'm going to get what I had before, but I'm going to multiply it by 3/6. So I have 5 times 4 over 6 squared, and now I'm multiplying it by 3 over 6. So you can see what the pattern is here, right? I have a falling factorial that's happening on the top, and on the denominator, I'm getting powers of my set A of possibilities for 1 die. So now the question is, what's going to happen when I end up with 7 die? So this is going to be interesting. What happens when I end up with 7 die? Oh, I've got so many matches. Let's try that again. So 7 die. I've got so many matches. Why is it that I'm guaranteed, no matter how I do this, to get matches? Well, the first one can be any number. The second one could be any different number. The third one can be any different number. The fourth one can be any different number. The 5th one can be any different number. The 6th one can be any different number. And now the 7th one has to match one of these by the pigeonhole principle. And what's going to happen is I'm going to end up getting 1 minus 6 out of 6. I have eliminated 6 possibilities, so I have 1 minus 6 out of 6, which is multiplying by 0. That is going to kill my probability if I have 7 dice or anything more than 7 by the pigeonhole principle. So we can actually compute that and we can figure out what these numbers are. But it's maybe a little more exciting when we do it in the context in which this problem generally arises. This is usually called the birthday problem. Some people call it the birthday paradox, but it's only a paradox if you don't understand probability, which you will by watching this video, so we'll call it the birthday problem. When 23 people get together, there is a 50% chance 2 of them share a birthday. That's the statement. That seems remarkable. That there's a 50% chance that 23 people, that's the size of a regular classroom, right? 23 people, so the chances are better than half that 2 people in our class share a birthday. Why is that? So it's only a paradox until you don't understand it. So we can go through the same analysis that we did here, right? So we're going to make some assumptions, first of all. We're going to assume that no one's born on leap day, because, you know, that one doesn't happen so often. And let's also assume that every birthday is equally likely to happen. That's also not a realistic assumption, but more on that later. So we can come up with a formula for the probabilities the same way that we've done here. So let's take n, and we're going to take p of n is going to be the probability that among n people, no 2 have the same birthday. This is no birthday coincidence. Okay? If there's 1 person, it's guaranteed. 2 people aren't in the room, so 2 people don't have the same birthday. If it's 2 people, well, let's just think about the same analysis we did here. It's going to be the second person just has to be anything other than what the first person was. So we divide by 1 over 365. And what about when we have 3 people? Well, we're going to take this probability, so 1 minus 1 over 365, and we're going to multiply it by 1 minus 2 out of 365. 365, that's how many days in the year. Don't match the first person, don't match the second person. That's what happens with 3 people. And we can keep on going like this and fill out the whole table. But the upshot of it is that we can actually get a really nice formula just from the same way that we generalized it before, right? So P of n, what's the probability that among n people there's no birthday coincidence? Okay, it's sometimes easier to count the opposite of something. So this is going to be the product from k equals 1 to n minus 1 of 1 minus k divided by 365. So why the n minus 1? Well, because you're going to have n minus 1 of these terms because the first person gets to have whatever birthday she wants. But everybody else has to not match all the people who came before them. Okay, and they're going to be k of those people. Another way that we could write this is often a convenient way, but another way that we could write this is 364 falling factorial, if you remember about those, n minus 1 divided by 365 raised to the power n minus 1. So on top we have the falling factorial, and on the bottom we have the exponential. So we can plug in into a computer. It's happy to spit out answers for us. And so when we put in 22 people, what do we get? We get 0.52. And when we put in 23 people, what do we get? We get 0.49. And keep in mind, this is the probability. This P of n is the probability that there's no birthday coincidence. So we want to take 1 minus P of n is equal to the probability of a coincidence. And so we can see that right here, 1 minus something less than half is going to be more than half. So once we have 23 people in a room, there's a better than half chance that 2 of them are going to have the same birthday. And notice this is a much different question than if I ask how many people do I have to get into a room in order to have a chance that they have my birthday. So if I pick a specific birthday, that's like saying I want these 2 to come up double 6s. Right? That's a very different question. It's much less likely to happen. Here, I'm not constraining what the birthday is, only that 2 people are the same. So this is the birthday problem. When you get 23 people in a room, there's a 50% chance 2 of them share a birthday. With 40 people, your chance of a birthday coincidence is 89%. So back when we had classes with 40 students in a room, it was a really fun joke that a lot of the professors did to bet the class, grades on the final or something, that 2 people in the room had the same birthday. And as long as you had pretty good attendance, you were pretty guaranteed that 2 of them would.